Hello friends, in this lecture we are going to learn about Schrödinger equation and particle in a box. As discussed in the previous lecture, Drude model, which is based on classical mechanics, fails to explain certain things like negative sign of the Hall coefficient, heat capacity of electrons, etc. We need quantum theory for that. In this lecture, we are going to learn the basics of quantum theory. We learn the fundamental equation, that is the Schrödinger equation, and apply it to solve particle in a box problem. We can start classical mechanics from Newton's second law of motion. Similarly, we can start quantum mechanics from Schrödinger equation. Feynman once stated that, I think I can safely say that nobody understands quantum mechanics. In this course, we shall not even attempt to understand everything in detail. Rather, we shall focus on getting used to the formalism of quantum mechanics and solve some important problems using this formalism. In classical mechanics, state of a particle is given by its position and its momentum. We solve Newton's second law of motion, m d2x dt square equal to f, with this initial condition x0 and p0, and we get xt and pt for all future time. Similarly, in quantum mechanics, state of a particle is given by wave function psi x of t. We solve Schrödinger equation and we are given some initial condition psi x0, and we can get psi xt for all future time. So we have to solve this equation. We don't know what is h at the moment. However, you can think of a modified 1D diffusion equation, which looks like this: IH cross del psi del t is equals to alpha del 2 psi del x square. Such equations are solved by separation of variables. So if we replace psi of xt in this equation, what we get is the following: I h cross psi d phi by dt is equals to alpha phi d2 psi dx square. Now divide both the sides by psi times phi. Divide by psi times or phi times psi. So if we do that, what we get is IH cross 1 by phi d phi by dt is equals to alpha into 1 by psi d2 psi dx square. And now you see, this is the time dependent part and this is the space dependent part, and they have to be equal to some constant, which is written as E. Now, from this equation, what we can write is I h cross 1 by phi d phi by dt is equals to E, and we can solve the time dependent part as phi goes as e power minus I e t by h cross, and the space dependent part we can write as alpha d2 psi dx square is equals to E times psi. And keep in mind that in this slide we have assumed that alpha h equal to alpha times d2 dx square, and this part is known as the time independent Schrödinger equation, and we can write that as h psi is equals to E psi. Note that this is some eigenvalue problem because this is some operator, this is some differential operator, and it operates on this function psi, and I get some constant times the same function. That means this is an eigenvalue problem, and we have to solve psi x and e using suitable boundary condition. Once we do that, then we can write the time dependent wave function as psi of xt is equals to psi of x times e power minus iet by h cross. In classical mechanics, we solve for x of t and p of t and get thermodynamic quantities depending on xp. And these things are solved from Newton's second law of motion. Now, what thermodynamic quantities we are talking about? For example, we can think of total energy, exp. Potential energy is a function of x. For example, total energy of harmonic oscillator V of x is half kx square, and this is the kinetic energy part. In quantum mechanics, variables are replaced with operators. So instead of solving for position and momentum, what we have to do is that we have to define something called momentum operator, which is given by this minus I h cross ddx. So this is some differential operator. Or you can define something called t square operator, which is minus h cross square d2 dx square, again some differential operator. Similarly, you can define something called position operator, which is just a function x. You can define some operator for energy, right? And that operator is known as the Hamiltonian operator, which is h, and this is the kinetic energy operator minus h cross square by 2m d2 dx square. This is some differential operator, and this is the potential energy operator. So thus, in this slide, we have defined the operator h as this, and the exact form of time independent Schrödinger equation is minus h cross square by 2m d2 psi dx square plus v of x psi of x is equals to e times psi of x. In quantum mechanics, the first thing that we have to solve is time independent Schrödinger equation, and we get the eigenfunction psi of x and eigenvalue e by doing that. So once we have solved that, then we can write the time dependent wave function as psi xt is equals to psi x times e power minus iet by h bar. These are known as the stationary states. Okay, let's see why. So what we do after getting the wave function? What we can do is that we can define something called probability density Pxt, which is given by psi star xt times psi of xt. Then we can get the position expectation value. So this is given by psi star of x times the position operator, and then we have psi xt dx. Okay. Similarly, we can get the momentum expectation value, and that is given by psi star x, and this is the momentum operator, and this is the psi x dx, and you have to calculate the integral. Now note that although the wave function this depends on time, however, if you calculate the probability density or if you calculate the expectation values, then this part e power minus iet by h cross, this cancels out because I have psi star and psi. Okay, so that will cancel out the time dependent part, and that is why these are stationary states. However, what we have to do is that we can define the general solution like superposition of many stationary states, and if you do that, then you get something like this, and then this is not a stationary state anymore, because now if you calculate psi star psi, the time part will not cancel out. Note that in this equation, En, these are the allowed energy levels, which is determined by the boundary condition. Cn's, these are the constants, And these are, of course, the eigenfunctions. In classical mechanics, given initial condition x naught, p naught, position and momentum of a particle is known exactly at any point of time xt, pt. However, in quantum mechanics, we go for some statistical interpretation and define some probability density. Now, if you look at this picture, the probability of finding the particle is more here. The probability of finding the particle is less here. Now, suppose you measure the position of the particle at some point of time, and then you find the particle to be here. Now, you can ask the question, where was the particle just before the measurement was done? The answer is nowhere. The act of measurement forced the particle to take a stand. This point might not be clear at this point of time. However, you must appreciate that there exists some indeterminacy in quantum mechanics. What happens when we make some measurement? The wave function collapses, shown by this dotted line, immediately after the measurement. Now, there is another kind of uncertainty in quantum mechanics. Unlike classical, we cannot measure position and momentum very accurately simultaneously. If we measure the position very accurately, momentum measurement becomes inaccurate and vice versa. Consider the two wave functions given in this picture. First one is a single wave and the momentum is fixed. We can use this lambda is equals to h by p. If I have a single wavelength, then p is fixed. Second one is a superposition of 10 sine functions. For example, if we superpose all of them, sine x, sine 2x, and if we take 10 such terms, then we get this picture. Now, if you ask where is the particle, now its position is somewhat localized. However, we cannot tell what is its exact momentum, because since it is a superposition of so many waves, I don't have a single lambda. So that means if I measure the position somewhat accurately, the momentum measurement becomes inaccurate. And it is impossible to go beyond certain limit when you are measuring simultaneously the position and momentum. And the limit is given by the Heisenberg uncertainty principle. Delta x, delta p, it cannot go to 0. So it is greater than equal to h bar by 2. Now let us solve for particle in a box problem. So you can imagine that this is some one-dimensional box and a particle is confined within the box, and it can move along this direction or it can move along this direction, and then it collides with the wall and it travels back. Since the particle cannot escape from the box, we have infinitely high potential at the box edges. However, inside the box, the potential is 0. So let us write the Schrödinger equation, the time independent part of it. So h cross square by 2m d2 psi dx square plus v of x psi is equals to e psi. And inside the box, v of x is equals to 0. So we can write d2 psi dx square is equals to minus 2me by h cross square psi, and this term we write it as k square, so we can just write it as minus k square psi. Now a general solution is given by this. It is very easy to verify that this will be a general solution, because if we take a derivative of cosine or sine twice, we get a minus sign. Okay, now because of the boundary condition, which is given by psi of 0 is equals to psi of L is equals to 0. So that means the wave function must go to 0 here as well as here. And because of the boundary condition, we see that A has to be equal to 0. Thus, the wave function is given by psi of x is equals to B sine kx. Now, we can use this part of the boundary condition, which tells that psi of L is equals to B sine KL is equals to 0, and which implies that sine of KL is equals to sine of n pi. This implies that K of n has to be equal to n pi by L. Thus, we have solved for the eigenfunction, and we can write psi n of x is equals to B sine n pi x by L. Since wave functions are related to the probability, they must be normalized. That implies that they must satisfy this. So we write the eigenfunctions, and let's sine square n pi x by L dx, and this integral should give us 1. So now we can write it as this is like 1 minus cos 2 pi nx by L dx is equal to 1, and this part of the integral is going to be 0, which implies that b square by 2 times L is equals to 1, and that gives me the constant b, which is equal to root over 2 by L. Thus, the eigenfunction is written in this form. We have solved for the eigenfunctions, and we know that k square is given by this, and the values of k are given by this. So from these two equations, we can solve for the eigenvalues. Thus, En is equals to h cross square kn square by 2m, and now we know the allowed values of k are given by this, and thus we can write this is equal to h cross square n square pi square by 2m L square, the eigenfunctions as well as eigenvalues. Now let us plot a few eigenfunctions. So if you plot psi 1, so this is psi 1, this is psi 2, this is psi 3, and so on. And one thing you can note that psi 1 has 0 nodes, psi 2 has 1 node, and psi 3 has 2 nodes, and so on. So what is a node? Where the wave function crosses this 0 line. Note that the wave function is 0 at the boundaries, but we don't count them as nodes. Only if the wave function crosses the 0 line inside the box, those things are counted as nodes. Now, once we have solved for the eigenvalues and eigenfunctions, we can write the time-dependent wave function in terms of the eigenfunctions and the eigenvalues. Let us try to plot the probability density and understand the difference with the classical description. Classically, how does the probability density look like? Classically, the particle is equally likely to be found anywhere inside the box. Thus, the probability density is given by 1 over L. However, the picture is very different in quantum mechanics. For example, if you look at the ground state wave function, then the probability density is the highest in the middle of the box. So if you look at the first excited state, then the probability density is very high. At these 2 points, if you look at the second excited state, then the probability density is very high at these 3 points and so on. So unlike classical, the particle is not equally likely to be found anywhere inside the box, but the probability density is very high at certain points. However, if you look at some high energy, then you see that the probability density appears to be more equally distributed inside the box. Thus, if we go to very high value of n, the quantum mechanical probability density will resemble the classical probability density. Now, let us calculate some expectation values, and we start with position expectation value. The wave function is given by this. The position operator is just a function x, and we can also define square of position operator, which is given by a function x square. Now, how do we calculate the expectation values? So, position expectation value is given by psi star times the operator times psi dx, and we have to find the integral 0 to L, and that turns out to be L by 2. Similarly, the expectation value of x square is given by psi star, the operator, psi, and then you have to calculate the integral, and that turns out to be this. Now, we can define delta of x, which is given by x square and x bar square, which is equal to square root of L square by 3, L square by 2 pi square n square minus L square by 4. And that turns out to be this number. And you see that the position uncertainty is proportional to L. That means wider the box, there is more position uncertainty, which makes perfect sense. Next, we calculate momentum expectation value. We know that the momentum operator is given by minus IH cross del x. So this is some differential operator, and similarly, we can define square of the momentum operator, which is given by minus h cross square del 2 del x square. Now, how do we calculate momentum expectation value? So this is given by psi star, the momentum operator psi dx, and we have to calculate the integral, and then this turns out to be equal to 0. Similarly, for p square, we write psi star, and then this is the p square operator psi dx, and if you calculate the integral, then this is what you get. Thus, we can define momentum, or we can write momentum uncertainty as p square average minus p average square, and that will just turn out to be, since this part is 0, this is just square root of n square, pi square, h cross square by L square. Delta P varies inversely with L. That means wider the box, less will be the momentum uncertainty. The expectation value of X, the expectation value of X square, the expectation value of P, the expectation value of P square. We also have calculated the position uncertainty as well as the momentum uncertainty. Now let us multiply them and see whether it satisfies Heisenberg uncertainty principle. So this is the expression for delta X times delta P. And you see that the minimum of this will occur at n equal to 1, and that turns out to be 1.13 times h cross by 2. Thus, uncertainty principle is satisfied. Now, you must have noticed that in case of quantum particle in a box, the expectation values are static. Why this has happened? Because we have used stationary states. However, if you look at classically, X and P does depend on time. So, can we get this time dependent picture in case of quantum particle in a box? The answer is yes, and let us see how do we do that. Before we solve the quantum problem, let us see what happens classically. So, the particle travels from one end of the box to the other end, and then it collides with the wall and comes back in this direction. So, if you plot the position of the particle as a function of time, so it goes like this. So, it moves from one end to the other and collides with the wall, and then it comes back. And if you look at the momentum, then the particle moves with constant momentum in this direction. After the collision, the direction reverses and the particle moves with negative momentum. Now we solve for quantum particle in a box. Just to simplify some algebra, we will take the box length to be equal to pi, such that the eigenfunctions look like this, and we defined omega of n as en by h cross, and that turns out to be equal to this. Instead of the stationary state, we take some wave function which is superposition of two or more eigenfunctions. So psi of xt, this is a superposition of the ground state and the first excited state eigenfunction. Now we can just write psi star is equals to 1 by root 2 psi 1 of x e power I omega 1 t plus psi 2 star I omega 2 t. And we have to use e power I theta is equals to cos theta plus I sin theta. Now you can just write psi star, and using this formula, the psi star will turn out to be equal to this. Now you see that the probability density is no longer stationary because I have a time dependent part. Let us plot P of xt at various different time. So at time t equal to 0, the probability of finding the particle is very high in the left hand side of the box, whereas it is very low in the right hand side of the box. As time progresses, the probability of finding the particle in left hand side of the box decreases, and the probability of finding the particle in the right hand side of the box increases. So at time t3, the particle is equally likely to be found in the right hand as well as the left hand side, and then even further, the probability of finding the particle is high in the right hand side and it becomes low in the left hand side. So it appears that as if the particle is moving from left hand side to the right hand side of the box. Now you can calculate the position expectation value using this formula, and then you will find that even the position expectation value, that also depends on time, and if you calculate the integral, this is what you get. And if you plot this, then you see that as time progresses, the particle is traveling from left hand side to the right hand side, and it suffers a collision at this point, and then it starts moving in the opposite direction and it comes back. This is unlike the stationary wave function, where the position expectation value is not a function of time. This remains constant along this line. Let us see how to solve a general initial value problem. State of a particle at time t is written using the eigenvalues and eigenfunctions in this manner. Now, psi n and En are solved from time-independent Schrödinger equation for a given potential and boundary condition. Now, the question is, how do we get Cn? We get Cn from the initial condition. Before we solve a problem, we need to know one important property. Eigenfunctions are mutually orthonormal. So this implies that if we take two different eigenfunctions and then if we calculate this integral 0 to L sine m pi x by L sine n pi x by L dx, that will turn out to be equal to 0 because m is not equal to n. M and n, both of them are integers, but they are not equal. However, if m is equal to n, then this integral 0 to L sine square n pi x by L dx, that will turn out to be equal to 1. Now we start by writing the wave function at time t equal to 0. So if you just put t equal to 0 in this equation, what you get is psi x 0. This is no longer a function of time. This is just a function of x, and that will turn out to be sum over n Cn psi n of x. So now let us see that using this orthonormality condition, how do we get these constants Cn? So we write f of x is equal to sum over n Cn psi n of x. And what we do is we multiply both the sides by this. And then we calculate the integral. Now we know that this part of the integral, that is delta of mn. So we can write this as sum over n Cn delta of mn. Now you see only the term m equal to n survive. Okay, so in that case, we can just write c of n as integral 0 to L f of x psi n star x dx. Note the similarity of whatever we have done so far with the Fourier series. Let us solve a problem of particle in a box having initial condition this. The initial condition is plotted here. We know that in case of particle in a box, the eigenfunctions are given by this, and again we have assumed L equal to pi. Then we can calculate this constants Cn, and it turns out to be equal to this. Now you know that cos of n pi is equals to +1 for n even, and this is equal to -1 for n odd. Thus, the even terms will cancel out and the odd terms will turn out to be like this. Now, we write the psi of xt as superposition of all the stationary states. So this turns out to be C1 psi 1x times e power minus I omega 1t, and then the C2 term is 0 because the even terms are 0, and then we get like C3 and so on. And in the compact form, we can write it like this. Let us take only two terms in the expansion, the ground state and only one excited state. Keep in mind that we are using L equal to pi. In that case, the probability density looks like this. Not surprisingly, the probability density equation looks very similar to what we did before, but the plot looks different. So mod psi n square, this is the amount of stationary state psi n within the total psi. And then sum of all the terms should be equal to 1. So in this example, if you calculate C of 1, then you will find that C of 1 square will turn out to be 0.9986. That means the particle is almost entirely in the ground state and very less amount of it is in the excited state. That is why if you plot P of xt as a function of time, it appears that all the probability densities, they look very similar to the ground state probability densities. Let us calculate the energy expectation value, which is given by psi star, the Hamiltonian operator, psi dx, and you have to calculate the integral. Let us prove that this is something which is time independent. So we just work with only two states and write psi xt as C1 psi 1 of x e power minus I omega 1 t plus C3 psi 3 of x e power minus I omega 3 t. So now we can write the energy expectation value as, so first we have to write psi star, so that is C1 star psi 1 star e power I omega 1 t plus C3 star psi 3 star e power I omega 3 t. This times the Hamiltonian operator times the C1 psi 1 e power minus I omega 1 t plus C3 psi 3 e power minus I omega 3 t dx. Now note that h times psi 1 is equals to u1 psi 1, right? So we can just write h psi 1 is equals to u1 psi 1 and h psi 3 is equals to e3 psi 3. So if we do that, then we find that this is equal to mod C1 square E1 and then we have psi 1 star psi 1 dx plus mod C3 square E3 integral psi 3 star psi 3 dx. Now you have some other terms which will have psi 1 star psi 3 dx and psi 3 star psi 1 dx. Because of orthonormality, these terms go to 0. And again, because of orthonormality, this term is equal to 1 and this term is equals to 1. So, which implies that H is equal to mod C1 square E1 plus mod C3 square E3. Now, you can take any number of terms and then derive this. Now, you notice that this is time independent. So, does it mean that every time I measure the energy, I get the same value? The answer is no. If we do energy measurement, then psi xt will collapse to one of the stationary states. So that means the psi x2 will collapse to either the ground state or the excited state. And then I measure the corresponding energy E of n. State of the particle before I do the measurement is not a relevant question. You do many such measurement and calculate the energy expectation value. Let's assume that C1 is equals to root 3 by 4 and C2 is equals to root 1 by 4. And now if you do the energy measurement 100 times, then you are expected to get the particle in ground state 75 times and in excited state 25 times. Now you calculate the average and then you will get this number. Thus, mod Cn square is nothing but probability of getting an eigenvalue En in a measurement. Let me summarize whatever we have done in the lecture. So, how do we solve a quantum mechanics problem? So, first step is you solve the time independent Schrödinger equation. You solve for eigenfunctions as well as eigenvalues. Now, using the eigenfunctions and eigenvalues, you construct the time-dependent wave function, which is given by this. Eigenfunctions are mutually orthogonal, and using this orthonormality or orthogonality, we get the values of Cn from this equation. Now, once we have Cn, we know what is psi of xt, the wave function. Now, position expectation value now can be calculated by using psi star times the position operator psi dx and calculate the integral. Similarly, you can calculate the momentum expectation value if you use the momentum operator. Now, energy expectation value is given by sum over n Cn square n. And mod of Cn square is probability of getting an eigenvalue En in a measurement. And if you add all of them, you get a number equal to 1. Energy eigenvalues and eigenfunctions will change depending on the potential and the boundary condition we are using. Rest of the steps remain exactly same. So let us solve for different potentials and boundary conditions.